At any time, there is a location on Earth where the wind is not blowing. This profound statement is what we proved today. And what is the mathematical interpretation of that? Let me first write it down. The Earth is, or the surface of the Earth is S2, the two-sphere. The question is, how do we interpret the wind? So the wind at a given location is given by its direction and its intensity. So it's a vector, it's a tangent vector for the two-sphere. Here's the two-sphere, and then let's say, I don't know, for example here, the wind is given by a vector which is tangent to the two-sphere.
So we assume the wind doesn't blow from top to bottom.
Yeah, that's true. That's what we assume in this model. And a tangent vector like that is perpendicular to the vector or the line that we draw from the center of the sphere to this point. For any continuous vector field, we assume that the wind or the wind distribution is somehow continuous, makes sense. So for any continuous vector field on S2, there is a zero. So a vector field is here a map from S2 to R3 such that the vector in R3 that you get at a point X is perpendicular to this line from the center of the sphere to this point. So the condition is that the standard scalar product is 0 for all x in S2. There is a 0.
So our imagination wants to place this vector in R3 at the point of the sphere, right? But we are thinking, but now mathematically the vector lies at the origin of R to the 3. It's sort of the parallel transport along this radial line to the origin.
You're right, you're right. So this is a statement we want to prove. This is now a precise statement, and we prove this statement with topology. We actually prove a more general statement also about higher dimensional spheres, not just about S2. To prepare this, I need a lemma about self-maps of the sphere. So we're looking at even dimensional spheres. And for each self-map of Sn to Sn, there is a point in the sphere such that fx is either x or minus x, the antipodal point. We prove this by contradiction, assume that there is no such point. And under this condition I want to, or I can define two homotopies of f. Define the first one, x f at xt. It's basically an affine linear homotopy that I normalize so that it happens on the sphere. So for time 0, this is just the identity, the map x, and at time 1, we obtain f of x. This is a homotopy of the identity on S to f. Okay, so let's check that the denominator is never 0. So in the picture, if we have x here, that's our sphere. And fx here, then if t goes from 0 to 1, we just follow the line in the sphere from x to fx. And this line should not go through the origin, and it goes through the origin in a situation where fx is the antipodal point. So if fx is here, antipodal, so fx is equal to minus x, then we would go through 0, but this we avoided. Fx is never equal to x and it's never equal to minus x, so this is well defined. The second homotopy is a homotopy from minus the identity to f. And it's not S2 as I've written here, but it's Sn. Okay, two such homotopies. What can we say about minus the identity? Because if that happens, then the identity on Sn would be homotopic to minus the identity. And we already discussed a bit how to compute induced maps of induced homomorphisms of self-maps of spheres. So what is minus the identity? Minus the identity is the composition of n plus 1 reflections.
Because the identity on Sn is in fact a map on R to the n plus 1, right?
Exactly. And inserting one minus sign in a coordinate corresponds to a reflection. So we have n plus 1 minus signs, so we can view this as the composition of n plus 1 many reflections. A reflection on Sn induces multiplication with minus 1 on the top homology. So hence, Hn of minus the identity on Sn is a map from Hn Sn, which is just the integers, to Hn Sn. It's multiplication with minus 1 to the n plus 1. And now we use the assumption that n is even, because if n is even, then this is odd. So n plus 1 is odd, so this is multiplication with minus 1. And this is a contradiction now, because the identity, of course, is just multiplication with 1. It's the identity also on homology. And therefore, minus the identity on the sphere cannot be homotopic to the identity, because they induce different maps on homology. And this is this interpretation of the fact that at some point, at every time, at some point on the sphere, the wind is not blowing. And we prove a similar statement now for Sn. Every continuous vector field on the n sphere vanishes at some point. And translation of this notion of vector field is that every map from Sn to Rn plus 1 with the requirement that the scalar product of tau x and x is 0 for all x in Sn vanishes at some point. So this is what we have to show. Okay, we want to apply the lemma. So out of this vector field tau, we want to obtain a self-map. And we obtain a self-map of the sphere by normalizing it. So we assume by contradiction that tau never vanishes. And then we can define the self-map F by tau x divided by its norm. Therefore, it lies on Sn. It's a continuous self-map of the sphere. By the previous lemma, we know that there is a point where fx is either x or minus x. Let's call it x0. This contradicts the fact that the scalar product of tau x0 and x0, which is it's the norm of tau x0 times the scalar product of fx0 and x0. And this cannot be 0 if fx0 is x0 or minus x0. Therefore, contradiction hypothesis was wrong, and we've proven that such a vector field always has a 0.
Mm-hmm. Can you show the lemma again?
Sure.
The statement of the lemma, yeah.
Yeah.
Mm-hmm. So actually, I think one can also sort of conclude it from the statement of the lemma, because let's say we now allow wind directions in every direction, not only tangential ones, yeah, then you can think of this map F from S2 to S2 as saying at every point on the Earth, where does the wind blow, yeah? But now you have a whole two-sphere of directions available, which are allowed. And then the statement is you will find some point where this direction, yeah, of the wind is either top or bottom.
Mm.
And that means, well, its tangential component must be 0.
Mm-hmm. Yeah, that's nice. Mm-hmm.